So now let's move on to the loss function again and try to gain some more intuition. And these are alternative to the original GANs objective function. And perhaps for some data set, least squares GANs is the one that is going to save you a lot of time. So it's good to know about it. The video is online, so I'm not going to spend too much time on it, but let's see what we are trying to achieve here. With the usual GANs, you're going to have a discriminator helping a generator train, but equivalently, if you go through the math, you're going to see that in practice, you're minimizing the Jensen-Shannon divergence between the actual data and the generated data, or actually the distribution of the data and the distribution of the generation process. But working with Jensen-Shannon divergence is not feasible. You're going to seek help from another function, your discriminator. It's not feasible because you don't know what is your PG, you don't know what is your P data. If you knew it, your problem was solved. You would just sample from that generative distribution. And that's the whole reason you're using a discriminator, because you don't know what is the formulation of Jensen-Shannon divergence. We know its formulation, we know its formulas, we don't know what is PG, we don't know what is P data. Let's try out another methodology. Let's get rid of this log. Let's get rid of the sigmoid in the end, which is going to give you probabilities coming out of your architecture, your discriminator. Let's get rid of those and then write down a mean squared error objective function. You want your discriminator to be close to a baseline. When it comes to real images, when it comes to generated images, it should be closer to another baseline. And let's set B to be 1 and A to be -1, or B to be 1 and A to be 0. And for your generator, you're going to go the reverse route. You're going to say that my generator should make my discriminator make mistakes. And you cannot call this D anymore a discriminator. Perhaps let's call it a critic. And then you want it to make the critic make mistakes and say that the generated images are something else. This is actually what we want. We want B and C to be equal to 1 and A to be equal to 0, or any other numbers should work. There is a theorem in the paper that if you set A to be -1, C to be 0, B to be 1, or even more general than that, if you set B and C such that B minus C is 1 and B minus A is 2, then out of this framework, using the same math that gave us Jensen-Shannon divergence for the original GANs, using the same math, you're going to end up with another distance, another divergence. And that's Pearson chi-squared distance or divergence. What is the idea here? There is nothing special about Jensen-Shannon divergence. Any other divergence should be perhaps equally as good, or perhaps better, or perhaps worse. And this is another divergence. But in practice, what you're going to be using is A to be 0, B to be equal to C to be equal to 1. That case is going to correspond to another divergence. We don't have a name for it, but it's going to give you a divergence anyways. And then the generated images out of LSGAN are at least as good as the ones coming out of DCGAN. And in terms of inception scores, they have higher scores. And then I was talking about mode collapse, and this is exactly what is going to happen. The underlying distribution is this. This is what you want to approximate. But as you try to train a regular GAN, after 15K iterations, you're going to pick one of the modes. You're picking this mode. Then after a while, you're going to just jump to another mode of your distribution, then another mode. This is how the training is going to process. And this is called mode collapse. It turns out that LSGAN for this example, or perhaps some other examples, is not suffering from it. Is everything clear? Any questions? Okay, awesome.